Hello there! This video is a recording of yesterday night paper reading that we did on my Discord. We read some paper, so yeah, enjoy and thanks. Bye! So yeah, let's start it. So segment anything and okay, so you made it. Nice. Can you hear me? Okay. Yeah, we were just getting started. So let's go ahead and read the abstract. We introduce the segment anything essay project, a new task model and dataset for image segmentation. Using our efficient model in a data collection loop, we build the largest segmentation dataset to date by far. Here there is a little bit of flexing by by Meta, with over 1 billion masks on 11 million license and privacy respective images. The model is designed and trained to be promptable, so it can transfer zero shot to new image distribution and task. We evaluated its capabilities on numerous tasks and find that its zero shot performance is impressive. Competitive with or even superior to prior. Oh my god. Competitive with or even superior to prior fully supervised results. We are releasing the segment anything model sum and its corresponding dataset SA1B of 1 billion mask 11 million images at blah 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 to foster research into foundation models for computer vision. Okay. So yeah, I think we all knew that already.
Yeah, I have one question. Like they say it's promptable.
Yeah.
What does it mean in that context? Because I don't yet. I heard they say it's promptable, but I don't understand how is it promptable. I can use it with points. I can use it with bounding boxes, but I cannot use it with like text prompts. So what does it mean?
Yes, so to me it means that you can pass something to it, right? So I think when we say prompt, we usually mean text, but I guess in general it means something that you can pass to. But it's just a gut feeling, but maybe we will know about it later.
Okay,
But
then I have one more question.
Mm-hmm.
Do you think that because the data set that they introduced, there is no label, there is only polygons in that data set. So you think that there is no label, like those are completely unlabeled polygons, or they just didn't disclose those labels?
So I guess if this is similar to interactive segmentation, when the task is like to just found a polygon, a mask around, an object, then I guess it makes sense. But I don't know about the data itself. So yeah, I don't know how they label it and how they gather the images, etc., etc.
I know
And who
one
did
thing
the
that,
label? Yeah.
yeah. So I know when they say we build a collection loop, that means that they have a system where they initially had people labeling manually, then they had a support for manual labelers, sorry, and then some of those images that we see in that data set, if you go to that website, are automatically annotated, like fully automatically annotated without any supervision. So this is what it is. So the only thing I know is some of those images, I have no clue how large part of the data set, but some of those images are absolutely annotated by system without any human in the loop.
Okay. Yeah, but like to me, it's kind of, I don't know. I don't want to say weird, but interesting. So I guess be able to annotate 1 billion polygons is an expensive process, right? And I kind of wondering why they are releasing this model fully open source? I mean, why are
In
doing
VR,
that? Yeah, I
in
mean
VR,
it's meta by the end of the day.
yeah.
Like they want, I mean, they actually need to make money now, right?
Yeah,
So
so
I
so
don't.
my theory is that they want people to use that model in VR systems to build like interactive applications that would, have some capabilities to interact with the surroundings, and you need to have some form of detection system. So they, I think, releasing it to build community around VR AI apps. That's what I'm thinking.
Yeah, yeah. I mean, probably that's true. And I also thinking if they are releasing this, I wonder what they are using internally, right? I mean, that I don't
Yeah.
know. Okay, so let's jump ahead to the introduction. So large language models pre-trained on web scale dataset are revolutionizing NLP with strong zero shot and few shot generalization. We all know that, right? The big GPT models, they work because they were trained on a lot of data, and these foundation models can generalize to task and data distribution beyond those seen during training. This capability is often implemented with prompt engineering, in which handcrafted text is used to prompt the language model to generate a valid textual response for the task at hand. Okay, in zero shot. Few shot. When scaled and trained with abundant text corpora from the text from the web, this model's zero and few shot performance compares so surprisingly well to even scroll bar, matching in some case fine-tuned models. Empirical trends show this behavior improving with model scales, dataset size, and total training compute. Foundation models have also been exploring computer vision, albeit to a lesser extent. I have no idea what this word means.
Me too.
This is some research vocabulary BS, I
Yeah,
guess.
you need to be exactly. You need
We
to
are not
use hard
smart
language.
enough to understand this. Okay. Perhaps the most prominent illustration, aligns pair text and image from the web. For example, Clip and Align use contrastive learning to train text and image encoder that aligns the two modalities. Once trained, engineered text prompts enable zero-shot generalization to novel visual concepts and data distribution. Such encoder also compose effectively with other modules to enable downstream tasks such as image generation with Tally. While much progress has been made on vision language encoder, computer vision includes a wide range of problems beyond this scope. And for many of these, abundant training data does not exist. Okay. In this work, our goal is to build a foundation model for image segmentation. That is, we seek to develop a promptable model and pre-train it on a broad dataset using a task that enable powerful generalization. With this model, we aim to solve a range of downstream segmentation problems on new data distribution using prompt engineering. The success of this plan hinges, another word that I have no idea, on three components: task.
Depends on.
Okay, okay. So task, model, and data. To develop them, we address the following question about image segmentation. What task will enable zero-shot generalization? What is the corresponding model architecture? What data can power the task and model? Okay. Uh, these questions are entangled and require a comprehensive solution. We start by defining a promptable segmentation task that is general enough to provide a powerful pre-trained objective and to enable a wide range of downstream application. This task requires a model that supports flexible prompting and can output segmentation mask in real time when prompt to allow for interactive views. Okay, so like here they are just saying that they need to find a good objective to make the model smart enough to be used in a zero shot or few shot. Uh, that seems what they're trying to say. And this thing in real time, this is kind of, I mean, it depends how you define real
It's kind
time.
of BS. It's
Yeah,
kind of BS.
yeah, I mean, like,
I later in the paper, I know I didn't read it, but I know that they have different versions because I was curious what is V8H and V B. So and there is also VL. So they
yeah,
have three different encoder sizes. And I was using the largest, the H one, which is apparently also the best, but not much better than L. But maybe the B size is close to real time, but the H size is like far from being real time. I was using that in Colab. I don't know.
yeah,
Maybe it was less than a second, but it wasn't like freaking 20 milliseconds or anything like that. So it was pretty slow.
yeah. B size, I think, should be around
Do you
50.
hear me?
Yeah,
Yeah. I'm curious.
I actually tried the model, and the main thing is that the image encoder is very slow. I mean, I think it's a VIT trained on 1000 by 1000 images, so that's very slow. And the mask decoder itself seemed pretty fast. I believe it was around 0.011 or something like that seconds on
okay.
3060. So
Mm-hmm.
that was decently fast. And I noticed that it's even faster. I mean, the entire pipeline, also considering the feature extraction, if you provide points or boxes as prompting instead of
Yes, for sure. Yeah,
letting
for
the
sure. There is a
model
difference.
figure it out by
Yeah,
itself.
yeah, yeah. So I noticed that also when you use like one bounding box and produce like single mask or maybe few masks because it's kind of like it is giving you more than one mask usually. But when you do it with the like prompting with the bounding box, it's faster. Question though, can I do encoding once and decoding multiple times with different prompts? So kind of like get halfway in and then prompt multiple time the image that is
If
already encoded
so, I
or
guess
not?
if they don't fuse stuff,
Yeah.
yeah, in theory, yes.
Okay.
Yeah,
Okay.
So, so
I believe you can do the feature extraction once. Maybe you use a YOLO model to extract the boxes, so a list of boxes, and you can use them as input all together in
Because I was
the
using
mask
the model
decoder.
and there is this Sam okay, there is this class that you use the general one. I don't remember right now the name. And,
Automatic,
and
semi-automatic,
there
something
is
like
the
that.
automatic, and there is this second one, this kind of like that you can use for specific bounding box, for example, extraction. And if you use
Uh-huh.
it, there are two stages. You have the stage where you have something like set image or something like that,
Yeah.
and then you have the stage where you basically call that to with passing the bounding box or something like that. So maybe the set image is actually the first stage, and that second stage when you just pass bounding box is the faster one. I'm not sure because for some reason they decided to have two-stage inference with set image and with actual inference. So I'm thinking maybe that's why. Maybe it's
yeah,
because they
probably.
want to give you this opportunity to prompt the same image multiple times without the time overhead. Yeah.
So
Yeah, most
for
likely.
context, VAT base has 86 million parameters. That is, I guess, similar to raster 101.
Mm-hmm.
The large 300 and the huge
Yeah,
600 million.
600.
And
Yeah.
I checked the source code for VAT. They are using just, they have implemented the attention itself in code, so they are not using the PyTorch one, so it's pretty slow by default, due to missing optimization. I don't know why they have done it, because I don't remember, but I don't think in the code I've seen a reason to not using the PyTorch. The multi-head attention in PyTorch. That is, it's faster in inference, and now with PyTorch 2 is faster in general. I don't know, man. I don't know. But yeah.
I mean,
Oh, okay. So the catch here, we need data and we need a good objective to train the model on the data, right? Okay. Unfortunately, there is no web scale data source for segmentation. To address this, we build a data engine. Here we iterate between using our efficient model to assist in data collection and using the newly connected data to improve the model. Okay. We introduce each interconnected component next, followed by the dataset we created and the experiments that demonstrate the effectiveness of this approach. Task. In NLP and more recently computer vision, foundation models are a promising development that can perform zero-shot and few-shot learning for new datasets and tasks, often by using prompting techniques. Inspired by this line of work, we proposed a promptable segmentation task, where the goal is to return a valid segmentation mask given any segmentation prompt. See figure 1a, that I guess is here. Okay, I guess image here, model, and different.
Yeah, and they show you that you can prompt with text, yeah, which is not possible, right?
Yeah, so you can't prompt with text, right?
Yeah, you can't, but they show you that you can.
Yeah, that's interesting. That's interesting. Yeah, and it's here, right? It's here. So
Yeah.
this is not a mistake, because the black hairs, I guess, is right here. So it's not like some random stuff that they just wrote here. This is made for this specific image here. So I don't know. Interesting.
Maybe that's the answer to what they use internally.
Yeah. If you're one of these guys or people, and you are creating this image here and you put these things, like it means that you probably have something, or you wish to have something that does this, right? And
They also show it on the website. If you go there, there is the GIF or the video, I don't know,
it's with
where they show you that you type cat and it highlights all the cats on the image. So yeah, I'm pretty sure it's some way possible. I know that you can use this with combination with like zero-shot detectors, like I don't know, like grounding Dino, for example, to get this effect. But it's combination of two models. Yeah. So.
Yeah. Weird, very weird. We were saying we propose a prompt segmentation task. Yeah, okay. A prompt simply specify what to segment in an image. Example, a prompt can include spatial or text information, of course, identifying an object. The requirement of a valid output mask means that even when a prompt is ambiguous and could refer to multiple objects, for example, a point on a shirt may indicate either the shirt or the person wearing it, the output should be a reasonable mask for at least one of those objects. We use the promptable segmentation task as both a pre-trained objective and to solve general downstream segmentation tasks via prompt engineering. Okay, this is a little vague.
Here is the most important part is this ambiguity acceptance. So this is pretty cool because what it does is I actually encountered that in one of the demos that I was doing. If you select point, let's assume that you are wearing a t-shirt with Adidas logo, for example, yeah? And you put point on that Adidas logo, it will give you multiple segmentation masks. One with that Adidas logo, one with your t-shirt, and one with the whole person wearing that t-shirt, yeah?
Makes sense.
So it kind of like accepts the ambiguity that it exists and it can be sure, and it gives you the ability to select which one is it, yeah? So it's better than what we have right now, where the model just picks something and you have no clue why. Here it gives you all of those, and it can, it gives you the ability to select which one you want. It's super cool, by the way.
Yeah, that's so cool. Okay, so the task, then the model, the promptable segmentation task, and the goal of real-world use impose constraints on the model architecture. You are imposing constraints on the model architecture, and then the goal of real world. Where are you supposed to use it in the matrix? I don't know. Okay. In particular, the model must support flexible prompts, needs to compute masking and amortized real time, okay, to allow interactive use, and must be ambiguity aware. Okay, so this is the thing that you were talking about. Surprisingly, we find that a simple design satisfies all three constraints. A powerful image encoder computes an image embedding. A prompt encoder embeds the prompt, and then the two information sources are combined in a lightweight mask decoder that predicts segmentation masks. Okay, we refer to this model as the segmentation if model, or SAM. By separating SAM into an image encoder and a fast prompt encoder mask decoder, the same image embedding can be reused. Okay, so this is the thing that we were talking before. With different prompts. Given an image embedding, the prompt encoder and mask decoder predict a mask from a prompt in 50 milliseconds in a web browser. Okay, I kind of wondering what this means, because this means, so assuming that your model is running on a browser, the speed just depends on the hardware or the computer. So this is not really.
Why would you test it on a browser anyway?
That's another question.
But that 50 milliseconds is only decoding, yeah? It's only decoding.
Yeah, but on which is this on
a
GPU?
I understand the question.
How is this a benchmark?
Yeah. But it's kind of cool because assuming that you have an application in which you store the embeddings of your data sets, I don't know, and then you can just reuse the embedding and just use the mask decoder, because I guess the embeddings that
load them from existing database, something like that.
Yeah. You need to have the same embeddings from this VAT, but this model, has been trained on a lot of stuff, so it can also be a very good embedder, I guess, compared to the clip model. I don't know, but
isn't that the purpose? Because that's what they mean by the foundational model, I believe. They want it to be used, to create those things, like embedding for other models later on, for example.
Yeah, but I guess they will have some plots with where they got the data, which kind of categories. So we can also have a look, I guess. Okay, so to make SAM ambiguity aware, we designed it to predict multiple masks for a single prompt, allowing SAM to naturally handle ambiguity. such as the shirt versus person example. Okay, so they were saying figure 2. Okay, well, I mean, yeah, it's just that. Let's see, data engine. To achieve strong generalization to new data distribution, we found it necessary to train SAM on a large and diverse set of masks beyond any segmentation dataset that already exists. While a typical approach for foundation model is to obtain data online, masks are not naturally abundant, and thus we need an alternative strategy. Okay, our solution is to build a data engine. We could develop our model with model in the loop dataset annotation. See figure 1c. So I guess okay, makes sense. Data our data engine has three stages: assisted, manual, semi-automatic, and fully automatic. In the first stage, Sam assists annotators in annotating masks, similar to a classic interactive segmentation setup. Okay, so like yeah, so probably like you have a very basic sum that can only like draw some mask, but that kind of shitty, and then you go ahead and you click the points, you say yeah, I don't want this region to be part of the polygon, blah blah. In the second stage, SAM can automatically generate mask for a subset of objects by prompting it with likely object location. Okay, and the annotation focus on annotating the remaining objects, helping increase mask diversity. So this means SAM can automatically generate mask for a subset of objects. So why just a subset of objects? So like how did they sample the data? So like maybe they start just with very specific type of mask, and then as soon as it was okay with that one, then
or maybe it is promptable with text and it understands, for example, some simple concept like text, like cat, dog, person, stuff like that. And those could be automatically generated for some, like they said, for subset of objects by prompting, yeah, which could mean like give me cats, dogs, people, yeah, and then the rest of the mask was generated manually for objects that were not recognizable with zero shot. I have no clue, but that would make some sense at least.
yeah. I mean, I guess it depends, like how you sample the data, right? So like assuming that you were doing the thing that you just said, maybe you will start with just images of some cat and dogs, right? And then you want images with, I don't know, llamas, a random species, and yeah, I don't know, but like I mean, they're not really telling too much here. Maybe they will tell more later. Yeah, in the final stage, we prompt some with a regular grid of 4 ground points, yielding an average of 100 high quality mask per image. Okay, and then the datasets, our final datasets, say 1 billion includes more than 1 billion mask for 11 million. Okay, okay. I mean, we we know this. I don't care here, honestly. We
The
still,
only thing that is important is that faces of people are blurred, yeah, and that's
yeah.
basically
Yeah, like images spans a geographically and economic diverse set of countries, and we found that some perform similar across different groups of people. This is interesting. This is probably the first time I'm seeing this, like in a famous paper, computer vision. Uh, the geographically and economically, because images on the web are usually coming from Europe and United States, like because in China we don't see too much of their stuff, or Russia, I guess, as well, and in Africa, I think they don't, have um, the how do you say, they're not as developed as uh, the Western world,
Like this, for example, looks completely different, yeah, in Asia versus Europe. Yeah. So I don't know, even something like window in the building can be completely
Yeah,
like
yeah,
visibly. Yeah.
yeah. Okay, so experiments. We extensively evaluate some. Okay. Uh, First, using a diverse new suite of 23 segmentation dataset, we find that some produce high quality masks from a single foreground point, only after slightly below that of the manually annotated grind through. Second, we find consistently strong quantitative and qualitative results on a variety of downstream tasks under zero-shot transfer protocol using prompt engineering, including edge detection, object proposal generation, instance segmentation, and preliminary transformation of test to mask prediction. Here we go. So yeah, preliminary. Yeah, sure. Uh, these results suggest that some can be used out of the box with prompt engineering to solve a variety of tasks involving object and image distribution beyond some strain data. Nevertheless, room for improvements remains, as we discussed in section 8. Okay, so I mean, we know, yeah. Uh, to me, one of the most interesting things that usually this model kind of suck is to be able, to find a line, you know. Um,
So I was testing that with I have an image of Leo in a leash. So
okay.
leash is
Yeah, I
very
know.
like long object, yeah. And it was pretty cool because when I was drawing bounding box on the leash, that leash was diagonal in the bounding box. So this is usually the main problem with segmentations, like long, thin objects
Uh,
that are close to 49 degrees, which means that the bounding box is basically like a diagonal of the square. And it was very good. It was very good. Like
that's cool.
it was pixel perfect precision. Sure, it was only one example, but I was actually looking for something like that, like you say, because usually those models stack with those objects.
Yeah, I really like how Meta is flexing here because I mean it's true
Those
that,
numbers, for
yeah,
example.
yeah, I mean it's true that you can cherry pick your images, but I mean, okay, how can you, I mean,
You have
it's
over
working.
if you scroll to the left, they show how many images there are.
Oh,
So it's over 500 masks
fuck me,
on a
yeah,
single image. So
yeah,
that's pretty fucking crazy.
yeah, it is, that's, yeah, that's so cool. Okay, pa, 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 pa. Okay, so now we
By the way,
go.
I have a question. Do you want? I can reach for a bit if you want to take a rest. No
So
pressure.
maybe I can. So maybe I can go till the middle, and then we do a quick break, and then maybe you continue. What do you
Okay,
think?
okay.
Would that make sense to you?
Yeah, I can do that. I haven't read anything out loud for like years, most likely, but I can try to read now.
It's interesting. I mean, so segment anything task. We take inspiration from, oh my god, Ubuntu, okay, from NLP, where the next token prediction task is used for foundation model pre-training and to solve downstream task via prompt engineering. Uh, isn't mask language modeling the foundation model pre-training task usually, right? I guess. Um,
Mm-hmm.
to build a foundation model for segmentation, we aim to define a task with analogous capabilities. Task. We start by translating the idea of the prompt from NLP to segmentation, where a prompt can be a set of foreground, background points, a rough box or mask, free from text, there we go again, or in general, any information indicating what to segment in an image. The promptable segmentation task then is to return a valid segmentation mask given any prompt. And again, the requirement of valid mask simply means that even when a prompt is ambiguous, it could refer to multiple objects. Yeah, we recall it. The output should be a reusable mask for at least one of those objects. This requirement is similar to expecting a language model to output a coherent response to an ambiguous prompt. We choose this task because it leads to a natural pre-trained algorithm and a general method for zero-shot transfer to downstream segmentation task via prompting. I really like how research paper, could just be a blog post, because they're always saying that the same thing all over again. Pre-training. The promptable segmentation task suggests a natural pre-trained algorithm that simulates a sequence of prompts. The promptable segmentation task suggests a natural pre-training algorithm that simulates a sequence of prompt point masks for each training sample and compares the model mask prediction against the ground truth. I'm not sure I am understanding what they're trying to tell me. So the promptable segmentation task, that is basically you give me a prompt, I give you a set of masks, suggests a natural pre-trained method, an algorithm, that simulates a sequence of prompts for each training sample and compare the model's mask prediction against the ground truth.
So I think it's like that. You take one image, yeah, and you prompt it with point, box, mask, and they should return the same result.
No,
That's what I'm thinking.
I think here he means that they create a simulation that that they create these things from the ground truth, right? So
Yeah. Yes. That's what I'm
okay,
thinking.
okay.
So it is simulation
Yeah,
because you have
yeah.
mask. Yeah, you have mask, so you can get the bounding box for that mask. You can get any point within that mask, and you can get, I don't know, sub mask of that mask. Yeah, some kind of
Yeah,
like subset of pixels. Yeah.
yeah.
So you generate them to train the model from those generated artifacts, but they are based on the label.
Yeah. So yeah, we adapt this method for interactive segmentation. So yeah, it's the same. It's similar. Although I like interactive segmentation, whose aim is to eventually predict a valid mask after enough user input. Our aim is to always predict a valid mask for any prompt, even when the prompt is ambiguous. Okay, this is a very big difference. This ensures that a pre-trained model is effective in use cases that involve ambiguity, including automatic annotation as required by our data engine. We know that performing well at this task is challenging and requires specialized modeling and training loss choices, as which we discussed in free. Zero-shot transfer. Intuitively, our pre-trained task endows the model. Oh my god, why they have to pick so much weird words? The model with the ability to respond appropriately to any prompt at different time, and thus downstream task can be solved by engineering appropriate prompts. For example, if one has a bounding box detector for cats, cat text segmentation can be solved by providing the detection box outputs as a prompt to our model. In general, a wide array of practical segmentation tasks can be cast as prompting. Completely true. In addition to automatic dataset labeling, we explored diverse examples task in our experiments in 7. I think we can skip this because here I think they are just talking about segmentation in general, I guess. Yeah, seems to just talk about segmentation in general. Discussion, prompting, and composition are powerful tools that enable single model to be used in a extensive way, potentially to accomplish tasks unknown at the time of model design. Okay, I think we can skip this as well, otherwise it's gonna take too much time. I want to know how they create the model. Okay, finally. Let's Ubuntu. Okay, let's see. So far so good, right?
Yeah.
Yeah. Yeah, it's kind of a bummer that every time you start reading, papers, they just, they have to be as much, general and full of
Boilerplate.
information as possible, that you kind of waste a lot of time at the beginning, right? Because like we could basically went directly here and probably we wouldn't have like missed a lot. Okay, segment anything model. We next describe the segment anything model SAM from promotable segmentation. SAM has 3 components, illustrated in figure 4. An image encoder, a flexible prompt encoder, and a fast mask decoder. I really like how they attach some words like a flexible and fast, right? So what flexible means that it can bend, and fast is fast on which kind of metric, we build on transformer vision models with specific trade-offs for amortized real-time performance.
This is my favorite, amortized real-time performance, whatever that means.
Yeah, and I actually know specifically which stuff they did because they based the VAT on another paper that is called VAT DET. That is a very cool paper in which they went ahead and ran a bunch of experiments, and they kind of, they tried to answer the question, hey, what will be the easiest and most effective way to build an object detector, using a VAT. And they also did a bunch of tricks, very easy stuff. But I mean, there is just one trade-off specifically, that in my opinion is not even so much of a trade-off, because like then you need to train a little bit more of parameters like to mitigate the effect of your trade-off. But yeah, image encoder. Motivated by scalability and powerful pre-train methods, we use mask autoencoder, right? Pre-trained vision transformer, VAT, minimally adapted to process high resolution inputs. And this, I guess, so this is the paper that I was talking about, exploring plain vision transformer backbones for object detection. This is kind of nice. The image encoder runs once per image and can be applied. Okay, so this is very interesting because they are using a pre-trained vision transformer, pre-trained with MAE. I hope that's the right pronunciation. But the data from which it was pre-trained is not very big. So my question is like, why are they not using the VAT from CLIP? That should be the best model that you can get. Like with the most powerful representation capabilities. So that's kind of interesting. So like to me, what I think they did is they say, hey, we have already take this model in Detectron 2, we will just use it, and then we will, try to motivate why we just use the code that we already have. But I don't know.
Isn't there any trade-off, like if they would use the one from the clip, it would be slower or anything?
It's the same.
Exactly the same?
is the same model plus a couple of tricks, but that won't change the weights of the model. So like the model will work, you just need to add a little bit of tricks. The only thing that will change is the positional encoding of the VAT, because clip was trained on a smaller image resolution, but I think in this case it's the same, because this I guess was super self-supervised train on ImageNet, I guess 22K or whatever it's called, like the big one. So still like has a small image size. And basically the trick that they do is like, I take an image, right? And then basically when I need to compute the attention on each token that I get, with a pet size, like sliding through the image, instead of computing the attention matrix on the full tokens from the image, I can go ahead and I divide the image in multiple sub images that in reality, you just basically compute the attention only on a subset of tokens. So basically, if I have a batch size, like if I have a tensor of a batch size of 1, and then I have 100 tokens computed from the images, then I would like to, okay, instead of doing attention on all the 100 token, I will do attention only on the first 50 and then the second 50. So like I shift, it's like I create a new dimension on the batch size. So like then I have 2, 50. So I can compute attention only on a small kind of subset, but then I can't attend to the middle parts of the images or like to the far extreme. So then I need somehow a way to fuse this feature. Oh my god, my explanation is very shitty, but maybe I can draw later. But yeah, I mean, it's, to me, it's kind of a cheap trick, but it seems to work. Yeah, the image coder runs once per image and can be applied prior to prompting the model. We consider 2 sets of prompts: bars, points, boxes, text, again, and then mask. We represent points and boxes by position encoding. Okay, some with learnable embeddings for each prompt type are free form text with an off-the-shelf text encoder from clip. Okay, wait, here there is something going on here. So we represent points and boxes by positional encoding, some with learnable embeddings for each prompt type. Okay, so like you have a learnable embedding for each prompt type. That kind of makes sense. So like I learn token for each of the prompt types. So I will have like a token for points, token for boxes, token for text, blah blah. But then how do you represent the bounding box as position encoding? I guess.
I don't know, maybe you just, convert that straight to text.
Yeah. Oh, but that's so clever, because so basically like you get a bounding box, okay? You somehow convert it to a positional encoding, right? So then you can sum it to the embedding to inject the knowledge of the position of the bounding box, right? That's kind of clever, I guess. Yeah, and dense prompts are embedded using convolutions and summed element-wise with the image embedding. Okay. The mask encoder. The mask decoder efficiently maps the image embedding, prompt embeddings, and an output token to a mask. Okay, the design is inspired by 14 with, let's see, end-to-end object detection. This is DATR, 20, specification thesis mask former. Yeah, employs some modification of this transformer decoder block. Yeah, let's see. Okay, followed by dynamic mask prediction head. Our modified decoder blocks use prompt, self-attention, and cross-attention in two directions. Prompt to image embeddings and vice versa. So our modified decoder. So this is there must be an image here. Okay, okay. So this is a decoder, right? So this is whatever you want to call it. So like the token, or some like in mask form and DATR, the things that comes inside the transformer decoder are called queries. So we can call queries. So yeah, you get the queries here, and then you get all the masks, but the number of stuff that you can get from a transformer decoder, is the same of the stuff that you place inside, because you get a sequence. I mean, you get a sequence of tokens as an input, and you will predict a sequence of tokens. So kind of wondering how they do that. It's very interesting that for the mask, they sum it. That's very interesting. Yeah. Yeah, I kind of want. Yeah, I mean, I guess it makes sense, because if you have, no, I don't know, like, why would you sum the mask? I mean, why a mask is sum, right? I mean, they say it's a dense prompt, right? But what the mask is telling you, so if I have a mask on something, it means that I just want to find the stuff inside that mask, right? That is the same thing with the bounding box. Like a bounding box can be actually converted to a mask if you want to, right?
Like, you mean like highlight every pixel and
Yeah,
say binding?
yeah. Yeah, I mean, it's a polygon at the end of the day, and a mask is a representation of polygon. So I kind of wonder, I mean, like, I kind of wondering, like, will the results be the same with, a box here, or a box as a mask? I don't know. And a point can also be represented as a mask, right? It's just maybe 4 pixels.
Maybe it's not enough information. That's what I'm thinking. Like, must give you too much information, and point gives you too little information. So for point, you
Yeah,
need to encode it,
yeah,
maybe extract more. And for math, you use convolution to, limit the size, yeah, lower the amount of
no,
value.
I mean, like, you're using a convolution here because you can take this and easily place it inside. So like, the nice thing about a convolution is that you won't need the position encoding, because the convolution is sliding a kernel. So like, it has as an engineering feature the fact that he knows where things are. So that's, I don't know. So this is Darcy. So maybe they did some experiments about that. It would be cool to see.
Maybe they will, disclose a bit more later.
Yeah, I don't know. I don't know. Okay, so we see the mask decoder. Okay, employed some modification on the transformer decoder block, followed by a dynamic mask prediction head. So I kind of wondered what dynamic means in this case. Our modified decoder blocks use prompt, self-attention, and cross-attention in two directions. Okay, prompt self-attention, it means that it's looking at all the prompts at the same time, right? And prompt cross-attention in two directions, so prompt to image embedding and vice versa, to update all embeddings. Okay, so it's cross attention, that is in two directions. So you cross attend the prompt to the image embeddings and vice versa to update all embeddings. What do you mean to update? I mean, what do they mean to update all embeddings? So why do you don't update the embeddings, right? They are fixed. And why?
I mean, I think that they just mean that you have some embeddings at the input you cross attend in one direction and the other direction, and then you have some result, and this is what you will use later on. So basically, you will use that.
I'm kind of wondering what is
Yeah.
so by vice versa. So I mean, if you cross attend, I mean, it depends on what you're using as a value in the attention, I guess. So maybe you first attend using as value and everything the prompts. No, wait. I don't know. Maybe they will have some better description. No. Right, so this is it. That's all the description they are giving to the architecture. So like it's one paragraph and that's it, right? Really? I mean, it's all this. I have so much questions, but okay, here they have something. So do they have an appendix? Oh, okay.
Like appending is like half of the paper. There's like
Okay.
10 pages of appending.
So this is the real paper. All the paper before was just a test to get to the real paper, right? So let's try to read this because I want to know how this thing is implemented, right? So because like we all know that it's working very well, but I want to know why it's working well. So so let's see, image encoder. Okay, we have seen that the image encoder outputs the 16 downscale embeddings of the input image. True. Since our runtime goal is to process this prompt in real time, we can afford a high number of image quality flops because they are computed only once per image, not per prompt. Okay. Follow standard practices. Okay. We use an input resolution 1024, obtaining by scale the image and padding the shortest side. The image embedding is therefore 64 by 64. To reduce the channel dimension following 62, okay, we use a 1.1 convolution to get a 256 channel, followed by a 3x3 convolution to also get 256 channels. Each convolution is followed by a layer normalization, and here it's pretty interesting because they are not using batch norm. Yeah, so basically, yeah, you get your features that if this is a VAT, it's gonna be 768 as a channel, let's say a featured dimension, embedded dimension on channel, and then you go down to 256. That in the original paper it was used as an input to a feature pyramid network. Yeah, here I'm not sure why they go down to 256. So this is interesting because it means that you are basically compressing the embedding to do all the other stuff, right? So if you are compressing the embeddings and this works so well, why you're not training your network with 256 as an embedding dimension, right? I don't know. So here this says parse prompts. So the bounding box, the point, the text, and yeah, are mapped to a 256 dimensional vectorial embedding as follow. A point is represented as the sum of position encoding of the point's location and one of the two learned embeddings that indicate if the point is situated in the foreground or the background. Okay.
How they know that?
So I think they are gonna classify a mask. I mean, so here we are two learn embeddings. So they are just learn Turing training. So it means that, you know, for these two embeddings, you're gonna to have an objective that penalize, you know, if something is a foreground and is predicted as a background. But in a kind of what? So probably they have a special, either a token or a position in the output in which they go ahead and map the background. If I remember correctly, in mass former, when you do the matching between the predicted mask and the ground truth, everything that is not matched is mapped to background. So I guess this is the way that they can train this learn embedding. Still interesting. Here is a box is represented by an embedding pair. The position encoding of its top left corner sum with a learn embedding representing top left corner, and choose the same structure but using the learn embedding indicated bottom corner. Okay, finally to represent free-form text we use the text. So I mean it means that the model is working with text, but they haven't coded that part yet in the repo, right? Because
Or they coded, they just didn't open source it. I think more likely.
yeah, because here they are specifically say we represent free-form text. We use the text encoder from clip, and text encoder is possible in general. With yeah, yeah. So they just yeah. So we should be able to use it. Okay. And dense prompt must have a spatial corresponding with the image. We input mask at a 4 times lower resolution than the input image. Then downscale on additional 4. Yeah, because like they need to downscale 60 times to match the embeddings. So 4 times 4 is 16. Yeah. Each layer separated by gateway activation, layer normalization. The mask and image embedding, and then added element wise. If there is no mask front, a layer embedding represents the mask is added to each image embedding location. Okay, this is also interesting. I kind of wondering like why do you need to add an additional prompt, like an additional embedding? Man, I have so many questions here. uh, and this is the lightweight mask decoder. So this was the prompt encoder. That is interesting. And the lightweight mask decoder. This module efficiently maps the image embedding and a set of prompts embeddings to an output mask. To combine this input, we take inspiration from transformer segmentation model and modify standard transformer decoder. Before applying our decoder, we first insert into the set of prompt embeddings a layer output token embedding that will be used as the decoder output analogous to the class token. Okay. For simplicity, we refer to this embedding, not including the image embeddings, collectively as tokens. Okay. The decoder design is following figure 14. So let's have a look. Okay. So image embedding. This thing here. mask decoder. Here the prompts are coming, so we have the output tokens plus the prompt tokens, and the output tokens are the ones that will be used output token, yeah, to make the prediction. We do the self-attention. Yeah, so basically it means that all the prompts can see each other. Then we attend. Oh, okay. So then the tokens attend to the image. Then they usually the multi-layer perception block, and then the image can attend. I mean, the image embeddings can attend to the tokens. Or like to be more precise, the image embedding tokens can attend to the prompt tokens. Okay, interesting. And then they attend again. Oh yeah. So then you take all the tokens that comes outside of this bad boy here, and all the ones that comes from here, I guess you concatenate together, and then you let them attend to each one of them, while you use the image to token attention. Yeah, you pass it to 2 times com transpose, so you increase the resolution, so this will go to, I guess, 64 times 4, I guess it's 2 times com transpose. Yeah, and then from this guy you get 2 things. IOU output token and output token per mask. Output token per mask. So now you just take the output token and you use it to do the dot product with the mask, and you basically gonna get the mask. And then you take the okay. So like you have two output tokens. So one is for the mask and one is for the IOU. I think in mask format they only had one, and then you output the IOU. Yeah, it's convoluted, but I guess it makes sense. But it's convoluted. What do you think?
Yeah, I don't understand half of those mechanisms, honestly.
I'm sorry.
I say I don't understand like half of those mechanisms. Basically.
Yeah, it's I guess it's a little bit of so like to me to me I think it's easier if you go from right to left. So like try to understand the things that you want to get, and then you navigate back. So like you want to get a mask, right? So you go here, and basically from this guy you get from the embeddings you reconvert the embeddings to be a sequence of tokens. So like you keep the 256, but you flatten here.
Yes, I understand. Every
Okay.
64 by 64 is becoming a single token, basically.
Yeah. So like a token has 256 dimensions, I say.
Mm-hmm.
And then basically you weight the tokens on the image based on the image to token attention based on the tokens that you provide. So let's call this the input, like yeah, the prompts tokens, right? So what you get here, it's the embedding that you had before, but weighted by the importance from the prompt tokens, right? And then you re-get to the spatial size, and you create a mask from that, and then you go ahead and you basically use this thing that you train. So like this is train, right? So this output token is not input by the user, it's something that you train to create some features that will dot product per mask. And I guess you have an MLP here either because you want to match the embedding size, but I don't think you need to because this should be 256, or maybe because just, why not? And then you obtain this mask here. So basically this is the embeddings weighted by the importance of the user stuff, and then how can you say that in English? And then conditioned on something that was trained to find the mask, right? I don't know if it makes more sense now. So like you need this because you need to have somehow a way to inject the fact that you want to find some mask in the embeddings. So like I could just not have this part here. I could just take the embeddings and place it here, right? And then I will train this to find the mask, and this will actually work. All these
Okay,
things.
So what do I have before that product per mask? So what is the
Here.
effect of 2x constant? Yeah, like kind of like intuitively, what do I have here?
So here, if you have the prompt tokens oh my god, you will have a sequence of image tokens. So let's call tokens because they are tokens that were weighted by the importance of each token to all the prompt tokens. So this is the same thing as if you want to do a translation, right? And here you have your sentence in French, and here you have the embeddings from the sentence in English. And then like you want to know how each word was important, its link is important to the sentence in French that you're trying to translate. It's the same thing, in which basically you just try to weight this big boy here by the stuff that the user provide to it. And if you don't have any tokens, so let's assume that we don't have the prompt tokens. So basically what's going to happen is that here we will just have the same stuff, right? Here we won't have this guy here. The only thing that we'll have here are the output tokens that are not sent from the user. So yeah, so like if you don't have the prompt tokens FEs, this is basically mask former without this thing, this IOU score. It's the same thing. Yeah. And the attention transformers are kind of cool because they allow you to just put some shit here and be able to somehow condition the thing that is coming into and attend to the stuff that you place. Yeah, I don't know if it makes sense.
Kind of. I mean, like I understand our explanation.
The thing that I don't understand is, why do I need to do token to image and image to token? So that's the only thing that is kind of so when they say image to
I'm
token,
not sure, but I was reading the grounding dyno, and they are doing the same.
yeah,
They are doing.
it's similar.
I'm not really sure if it was exactly the same. I mean, okay, no, maybe not exactly the same, but the same attention mechanisms were used, just in different order. And I'm curious, kind of like maybe it, the order of operations matter, in the sense that if you put the same vectors but in different order into that mechanism, they will mix differently. I'm not sure, but they
So
use the same
in this
mechanisms for
case,
sure.
yeah. So like in this case, it's
Just
just
not
a
two
question.
times, they use it 6 times, but the same blocks were used.
So in this case, the question is, from which uh, factor are the keys, queries, and values of the attention here and here computed? Because I'm gonna guess that here you get, here on this guy, so talking to image attention, on these guys you compute the keys and values from the prompt and the output tokens, but you keep the queries from the image embeddings. And here vice versa, I guess, because that would make sense. Yeah, because like basically the keys in the attention computation are called keys because somehow pull stuff from the queries. Uh, yeah, so I mean, where's, yeah, maybe if you look at the code, yeah, but I mean, this is actually flexible and lightweight in my opinion, because this is just two. Here you don't have too much stuff, to be honest. And if you remove the prompts, it's just going to work. If you, so yeah, so this is very interesting. So if you want to add a new prompt, you can just go ahead and add a new prompt. If you want to go ahead and add a new type of output, you can just go ahead and add a new token here, and then from here you are going to probably take it and predict something. So like assuming I want to predict the bounding boxes, uh, in a, just as a stupid example, I can just add a token here. I can take it from here. I can put it on a linear layer, and I can go ahead and predict some bounding boxes. It's gonna work like shit, but it's gonna work. And yeah, I'm kind of wondering the number of masks that they create, because here it looks to me, here I can see 256, so I'm gonna assume here I got 256 masks, but they say it's dynamic, so you should get more masks, I guess, because we were looking that, we were seeing more masks in the images before. So maybe here they say something. Okay, so self-attention on the tokens. Cross-attention from tokens as queries to the image embeddings. Okay, token to image. Yeah, but if the tokens are queries. Then it's image to token, I guess. Well, to the image embedding. A pointwise MLP updated token and cross attention from the image embeddings as queries to the tokens. This last step updates the image embeddings with prompt information and is this. So here we have the image embedding that are updated with the prompt information. During cross attention, the image embedding is written, okay. Each self cross attention and multi-layer perception has a residual connection, the normalization and dropout of 0.1 at training. The next decoder layer takes the update tokens and the update image embeddings from the previous layer. We use two layers decoder. Okay, so the next layer takes, the thing from the bottom and the updated image embeddings. So this thing here looks like. To ensure the decoder has access to critical geometric information, the position and encoding are added to the image embedding whenever they participate into an attention layer. This is the same thing as in massform and TR, and I guess also in grounding Dino. Additionally, the entire original prompt tokens, including their position encoding, are re-added to the updated tokens whenever they participate into an attention layer. This allows for strong dependence of both the prompt tokens, geometric location, and type. I'm not convinced by the need of doing this, but it's okay. After running the decoder, we upsampled the updated image embedding by 4x with true transpose convolution. Layer. Now it's downscale relative, okay. Then the tokens attend once more to the image embeddings, and we pass the update output token embedding to a small 3-layer MLP that outputs a vector matching the channel dimension of the upscale image embedding. Finally, we predict a mask with a special pointwise product between the upscale image embedding and the MLP output, and it's here. The transformer uses an embedding dimension of 266. The transformer and blocks have a larger internal dimension of 2044, but the MLP is applied only to the prompt tokens for which they are relative few, relatively greater than 20. However, in cross attention layer, where we have 60 by 60 image embedding, we reduce the channel dimension of the queries, keys, and values by 2x. To 128 for computation efficiency. Our attention layer uses for 8 heads. Okay, so yeah, this is also makes sense. So yeah, I a lot of empirical stuff. Here they have, as you can say, 256 is too big in this layer here, so we're gonna ahead and reduce it. I mean, for computational efficiency, okay. Our attention layer uses 8 heads. The transport convolution used the upscale to upscale the output image embedding are 2 by 2, straight 2 with output channel dimension 64 and 32. Have Chirus activation. They are separated by layer normalization. Okay. Now probably this is interesting. Like, how do they make the model ambiguity aware? I guess. Do you want to take a quick break?
Yeah, sure.
5 minutes break. I need to
Okay.
drink more. Yeah. See you in 5 minutes.
Yep.
So, I'm back. Oh, wait, where is my water? Oh boy.
You went for water and you came back without water. That's
1 sec, man. Okay, okay, okay. So I also open the source code, and I have to say, it's not too bad. It's not too bad. They have all the
with
types.
Right. I
around.
will need to drop off in like 20 minutes.
And
Book
yeah,
away.
yeah, yeah. We
Walk
can.
Leo and then kind of like wrap up everything. So yeah, but just letting you know so that you wouldn't be surprised when
No, yeah,
when I
yeah.
begin.
I want to be in bed in 20 minutes, man. So I say
Oh,
I
ambitious plan. Okay.
I am ambitious tonight. So I think like we got a good idea of what is going on, and from the architecture kind of.
Yeah, pretty stupid that you need to look for it in appendix versus having that
Yeah,
actually in the paper. It's
I mean
like,
I mean I guess except for how they collect the data, etc. This is the most important part. And
yeah,
still I think we don't know yet how the making the model ambiguity
yeah.
aware.
Let's take a look at
So
that
as describe
really.
a single input prompt may be ambiguous in the sense that it corresponds to multiple valid masks, and the model will learn to average over this mask. We eliminate this problem with a simple modification. Instead of predicting a single mask, we use a small number of output tokens and predict multiple masks simultaneous. Oh my god, come on English. By default we predict three masks, since we observe that three layers, whole part and subpart, are often enough to describe a nested mask. Whole part and subpart. Okay. During training, we compute the loss described shortly between the ground truth and each of the predicted masks, but only but propagate from the lowest loss. This is a common technique used for models with multiple outputs. Didn't know that. That's cool. 45. Okay. But only but propagate through the. Okay. We like to rank predicted masks, so we add a small head operating on an additional output token that estimates the IOU between each predicted mask and the object it covers. Ambiguity is much rarer with multiple prompts, and the free output mask will usually become similar. To minimize computation of degenerate losses as training, and ensure the single unambiguous mask receive a regular gradient signal, we only predict a single mask when more than one prompt is given. Okay, this is accomplished by adding a fourth output token from an additional mask prediction. This fourth mask is never returned for a single prompt and is the only mask returned for multiple prompts. Adding a fourth output token for an additional mask prediction. This fourth mask. Okay, not really. So I didn't understand in detail, but I guess the catch is that that by default that they predict free masks, and when you have more than one prompt, you only predict one. Yeah, only predict once.
It
Yeah,
was
simple.
muted. So what I saw is yeah, when you prompt it with bounding box, you will get free math, and they usually are very close to each other, very close. If you would kind of like
When more than
compute
one prompt
IOU.
is given, so if you give more than one prompt, you're gonna have one mask. So if you like do a bounding box and a
When
point,
I'm prompting with one bounding box, I got free math,
yeah,
which are different.
but here you see, uh, predict a single mask when more than one prompt. So assuming if you do like 2 points, then I guess you should receive one mask.
Okay.
I
And
guess.
also interesting thing, maybe, I'm not sure. I had this kind of like chart where I was doing full automatic generation, and I got a 64 mask, which is also interesting. Why I have no clue whether or not it was accidental or it returned 64 mask. Regardless, like I got 64 mask, which is coincidentally, the power of two. I just thought about that. But what is interesting, those masks were not. So there were some masks that are very close to each other.
Okay.
Even in full auto, I got like a. Can I send links over here somehow? I'm not sure. But interesting thing was those masks that I got in full auto. I got 64 of them, and some of them were like the same. So they were like copies of masks, like more or less very similar to each other. So that was also pretty weird. I didn't kind of like understand why is that happening.
But then, like, you should also get the scores for IOU, right?
So
You
you
can use
let me
them
just
somehow.
think about the. So what you get is okay. So when you run bounding box prompting, not full auto, you get three things. You get the masks, you get the score, and you get something called logits or logits.
Yeah,
I'm not really sure how to
yeah. I think it's just probably is just this part here, probably.
Okay,
I
because
guess.
it is multi-dimensional.
Yeah.
I don't remember exactly. Sorry, I don't remember exactly what was the shape of the numpy array, but it was multi-dimensional. And the score is obviously single shape vector, and the mask is like three-dimensional. Yeah, because and what is also interesting, they don't return PyTorch tensors; they return NumPy arrays, which is also I found it interesting that they decided to, to return, already NumPy arrays because, for example, the text-from-2, most of the libraries decided to return PyTorch tensors, and they didn't. It was also interesting.
That's interesting. I think. I mean, the source code model is definitely returning a PyTorch tensor. So I think the wrapper around that, they have something called sum predictor, and
Yeah, that was the one. And that one returned. Yeah, you
predict.
remember? I couldn't remember the
Yeah,
name. So
yeah,
some
I can see
return
that.
three,
Yeah, it's
couple
converting
of
to NumPy.
free NumPy arrays. Yeah.
It's doing the detach during prediction. That makes no fucking sense because if you are predicting why this is not in a no grad predict torch. Ah, okay, so they also have a function that is called predict torch, and that will give you, I guess, no, it's called internally. Oh yeah. So you can use a function called predict torch. That's yeah, but you need to do some. Yeah, this is weird, man. Why do you? Yeah. This is a little bit. Yeah, I mean they are called torch no grad. Yeah, but the nice thing about the code base, I'm looking at it now, is that they have actually some comments around, and they have some docstring. They have the types for each uh, parameter, and it's well organized. It's not bad. I'm impressed. This is the most impressive part for me.
It is the difference between open sourcing code done by large organizations versus a shit code created by some researchers at the university. I mean,
Yeah,
take a look at how the whole, like, I was speaking about it with somebody yesterday. Like, take a look how well, like, how polished was the release? The website with the data set, how does it look?
Yeah,
Like the
this is
website
why,
with
yeah,
demo,
it's
everything was polished, yeah, and
and
working.
this is why I don't understand why they're doing this.
Yeah, that can be open question for sure. But for me, it's clear that they had that model for weeks now, and they released it when they decided the right moment to release because everything else was super well prepared.
Yeah, like the demo, it looks like a product from a company,
Yeah,
right?
exactly. It looks like a product that you can sell, and
Yeah.
they, speak Apache 2 license on it. I was, so interesting. Uh, yeah, very interesting. I actually, other than VR, I have no other explanation for it.
Yeah.
Right?
Yeah, it's so weird. So weird. Like, yeah, I mean, they are probably thinking about some end game there, but uh, I cannot. I mean, so by the way, looking at the source code, they don't have a way to add the text, but if they use the clip text encoder, one can just go ahead and add it. But the issue, wait, let's see if somebody type text as prompt enhancement. Uh, looking if people. Oh, interesting. So, yeah, open some random stuff. Yeah, so the issue is that the tensor that you get from the clip text embedder or text encoder is not of dimension 256, right? Is probably, it depends on the model, but it can be 512, I guess, or 768. So they probably had, something in the middle to,
Adjust the shape. Yeah.
yeah, yeah. So yeah, then but it works really well. And about what about the
Edge
edge
prediction.
detection? Yeah.
Hmm.
How do you do the edge prediction with SAM? You need.
I think that they just convert math into polygons, yeah, and that's it.
I'm I'm not sure because here some parts are more bigger than 1 pixel. Or what do you think? I don't I don't know.
That was my understanding originally, but maybe I'm wrong.
By the way,
No.
it's pretty neat that the ground true, it's very chill. And here in Sam, you have so much, yeah, super chill, right? Yeah, Windows, who cares? Uh,
Yeah. Who cares who would spend time annotating this?
yeah, so yeah, this was cool. I think now I got a way better uh, understanding, so I can go ahead and nitpick people on LinkedIn.
Obliterate people in comments. Yeah.
Yeah, but
Yeah, but about the comment that was today or yesterday, I don't remember when you said it's pretty lightweight model you can train. Like the guy asked about fine tuning that model. You remember that comment? And you commented under my post. Remember or not remember?
yeah. I commented, but like, yeah. So
What
like,
do you think about that? Because for me, like trying to fine tune on your data set makes no sense. Like like the value that you have is that it is trained on such a large data set
no,
that it generalized super well. Like, why
Yeah,
would you train that on your own
yeah,
data set?
but like I mean, the point is that I mean you are fine tuning on which task because I mean you can just I mean you need this right because the old catch is that it has to be promptable. So you can generate points and boxes and masks from your ground truth, but then what's gonna be the goal there? I mean, you can do that. You can just like in theory,
Because
I
I
I
didn't
freeze
understand
this
why would you
right.
do that. Because people have trouble right now to understand that with those new, you know, how do you call it? Like
Foundational models, no.
the foundational models. You are not supposed to fine tune them. I don't think so. Like I don't think that's the right. Like everybody is like, oh, I
Like
need model. I need to train it on my own data set. I
so
don't think you
so
do in
so
those cases.
my catch is that if you say to me, hey, in this image, which is I mean what is the foundational model? I'm gonna say is the encoder. Here, the encoder, in my opinion, is the foundational model, and you can just go ahead and freeze it, right? But this thing, you know, assuming that you have very weird data, so let's assume that you really want to fine tune it, okay, like because you want to do
Mhm.
it, right? And
As you want to do, that's perfect reason. Yeah,
yeah.
that's, that's fine.
I mean, for some reason you want to do it. So I agree with you that if it's working well, I mean, why do you want to do it? Uh, but you know, it could also be, hey, I want it. So like, I can say, hey, this model is actually good at creating some mask. So maybe I can just, I can just re-initialize this and train only on my data, so it will be able to generate masks that only
Only
exist
masks for my
for my
classes.
data.
I don't know.
Yeah,
Okay,
yeah,
maybe. But
maybe I don't know.
question that I is, you looked in the store. Did they even release the code for training?
Oh,
Because I know that they released like kind of like the whole, you know, packaging for the model. They released the data set. They
wait a
released the
second,
weights.
man. So, but man, they have a some Onyx model in the code.
Mhm. You think
Interesting.
it's Sam? Is it this code?
No, no,
Is
no.
it this mode?
So okay, so they have a sum, so they have a sum model, and then they also have some Onyx model that is the same thing but slightly kind of different. And this is the model that you're supposed to use if you want to export it to Onyx. So that's cool. And now I don't see any train code. I can see scripts, export Onyx model, GG. Uh, Damn. But no train.
Interesting. Yeah, so that's another complication if you want to train it on your own data set. Like,
Yeah, but not even the loss function. Yeah, I mean, isn't this weird? And another weird thing is, this paper was not submitted to any conference. It was just placed on ArcSpin, right?
mhm.
This is very interesting. So, like in my
Like the
opinion,
reasoning, why is it all happen? That's
so
interesting.
so yeah, because like I mean, there are a lot of kind of red flags, you know. So first of all, all the very polished release demo, etc., then the fact that they don't have training code, and then the fact that they didn't submit the paper to a conference, they just place it on the internet and that's it. And yeah, I don't know, man, I don't know, but it's super cool. It's super cool that they also have a script to quantize it and export it to Onyx. So that's the first time.
Do you think that, if I can export it to Onyx, I can run it in Onyx runtime, I don't know, in browser, for example?
It depends how much preprocessing you need to do on the image, but yeah. But I mean, you can also go ahead and run it on your computer. It's gonna be faster, right? The thing is that I don't see half precision here somewhere, so maybe, yeah, maybe you need to set it by hand, I guess. But this is so cool. This is really cool, man. This is some good shit. I think I have some content for a very cheap but interesting blog post here, and I can try to benchmark it. I mean, I can try, but I need to find the right time, maybe or next week, to write a blog post how to implement this from scratch, just the model, because I have no idea about the loss function here. I don't think they talk about it. What is the loss function?
I mean, they certainly didn't in the part that we read. Yeah.
Loss and train. We supervise mask prediction with the linear combination of focal loss and dice loss using 14. We turn the proper simulation task using a mixture of geometric prompts. Simulating intervals top parameters. Okay. Oh yeah, I mean, that's okay. The thing is that we supervise the max prediction with linear combination of focal loss, yeah. But so, I mean, I don't think they had. I mean, this is the polygon they had, right, as a ground truth. How do you train the sub mask?
I mean, like.
So
I mean, this is the result, yes. So all of them are valid masks for them.
Yeah. But like you need to teach the model how to do this. So like assuming that you are training blah blah, and you are seeing.
So you talk about the loss. How do you
Yeah,
how do
because
you
like I say that they use
no
the
it
focal
is
loss and dice loss.
some form of IOU between masks. I don't know. Or
Yeah, but what
no,
is the
it needs
ground
to be
truth?
mask. Ground truth is the one that you are highlighting right now.
Yeah,
That's what I'm
so
thinking.
and then like how do you ensure that this part makes sense, or maybe you also have the.
I think that it makes sense if it is submask of the original mask.
Yeah, but everything can be a submask.
Yeah,
The
that's
issue.
true. That's true. But I can also tell you that what they show you here, which is kind of like this perfect mask, where what do I mean by perfect? Like in the results that I was getting when I was doing the demo, some masks were not coherent masks in the sense that, here every pixel touch another pixel belonging to the mask. You understand? And in the ones that I was running, like I got those perfect masks, but some of those masks that I got was kind of like random pixel here, random pixel there. They were not like connected to each other. They were like kind of like separate, like like islands on the original mask that I supposed to get. So kind of like I think that they kind of like cherry picked those examples where all of those masks like make some sense like intuitively, like, okay, this is the handle of the scissors. This is like one part of the handle of the scissors. But those maps that you get are not always like that. Like the common factors they see that they're like valid sub maps of the original map, but they don't always look like some coherent
Okay.
object.
So maybe.
I'm not sure if you understand what I mean,
No,
but
no,
like,
yeah. That was cherry pick.
yeah, I mean, like,
Close.
it's a paper, yeah, so
Cherry
it's
pick.
kind of obvious, yeah.
So do they say anything here about the?
Okay, so I need to drop off because Leo is pissed off. He is
Yeah, man.
behaving.
I need to go to bed. Cool. I think we learned really a lot. It was, man, 2 hours. It was pretty intense.
Yeah, I mean, like, I needed to go through it, yeah. So
Yeah,
it's much
but
better to
yeah,
go
like
through it.
I really think that, by myself, I wouldn't be able to have the motivation to read for
To
two
read.
hours straight.
Yeah, I was
And the
reading the grounding
questions.
dino, I guess, for 6 hours because it was like, okay, I need to take a break. Yeah, that was the theme of the day. It was like taking breaks from reading. Yeah, so I guess it's much better to sit together and do
Yeah,
it together because you have motivation to do it.
yeah,
Yeah,
yeah. Cool, man. Have a nice evening. I'm gonna
yeah, you
hit
too.
the bed. Cool.
You too. Thanks
Bye,
a lot.
man.
Thanks a lot. I hope
Thank you
we'll
for
we'll do it
joining.
more.
Yeah, sure.
Yeah, yeah, yeah. Okay.
Cool,
Thanks.
man.
Thanks a lot. Bye bye.
Bye. See you. Ciao.